welcome to this department seminar. It gives me great pleasure in welcoming Professor Subbarao Kambhampati, as Rao, as most people know him, to IITM. I think it's been a while since you gave a talk at IITM, though.
I think physically,
Yeah, physically.
Over Zoom.
Over Zoom, of course, yeah. Yeah, physically it's been a while since you gave a talk at IITM. So very quick intro to Rao. So Subbarao Kambhampati is a professor in the School of Computing and AI at Arizona State University. And yeah, I mean, there's a lot of fellowships and other things that he has. But more importantly, he has a much more difficult to achieve honor. He is our distinguished alumnus. Right? It's a lot more selective than some of the IEEE fellows and things like that. So we're very happy to welcome Rao on this. And so Rao is an award-winning teacher and a recipient of university-wide last lecture award. And he has also served as the president of the Association of Advancement of AI, AAAI, and then continued to serve in roles as past president, and has also been very instrumental in having the AAAI chapter of India starting. Right, so he's pushed for that in a big way, and he's also a founding board member of the Partnership on AI, and more importantly, he has been an inspiration for people of my generation. In fact, I start talking about giving public lectures on AI after looking at how active Rao was in engaging with public opinion on trying to build a narrative around AI, and is really active in fostering public understanding of AI technology and its societal impacts. And he has served on high-profile advisory panels for American, Canadian, and Indian governments, and is frequently quoted in prominent national and international media. And of course, if people are on Twitter, do follow Rao on Twitter. He has a wealth of information that keeps pouring to you. Right? And over to you, Rao. Thank you.
And also make it more accessible so that there'll be more questions, even if you're not exactly in my area. That's true. The symbols as a lingua franca for bridging human AI chasm in explainable and advisable AI systems. If you want just the meaning of the title itself, all I'm saying is irrespective of what sort of representations an AI system uses, whether it's using deep learning or deep learned representations or more symbolic representations, whatever, I don't care. When humans in the loop are interacting with it, that interaction better be structured in a way that makes sense to the humans. Okay, so I sort of feel it's a huge letdown after all the advances in AI, if we now have to also think about how the machines are thinking, right? I mean, it's bad enough that I have to deal with you guys as to what are you thinking, and if now every AI system I have to figure out how it's working, what it's thinking, it's just like civilizational failure in my view. If we are going to cohabit with the AI systems, they better do the heavy lifting. Why should we? Right? I mean, that's the way you should be looking at it. And so the point is that irrespective of what you do, you should have a symbolic interface as part of the interfaces to the humans, and through which you can take advice as well as provide explanations. You guys do that, first of all. You do realize that, right? I have no clue how you think. I don't know. Nobody knows what we do in our brains. But we have this sort of symbolic interface. Of course, part of the multi-modal interfaces, we do have this language. We talk and we use that to communicate. And AI systems need that too. So that's basically the bigger point. I'll get to that in a slightly roundabout way. Let me see if I can. Okay, so I'm sort of, I don't want to go through this too much, but I'm sort of a researcher in AI. I'm mostly interested in human in the loop, human AI interaction sort of issues of late. But as Ravi pointed out, I also on the side do this stuff about making sense of AI systems to a broader public, because it's become like, it's an area that has become, I have this tweet saying that there's never been more need for AI experts without any AI expertise, because everybody is an expert in AI, and so that sort of opens up major problems in public misunderstanding of what these technologies can do, and I do some of the, trying to explain our technologies to others, and that's kind of very useful. I think we should try to do that too. And I also, in addition to my own research, which I'll be talking about here, I also, within the AI community itself, there are, big shifts, pendulum shifts between symbolic versus, for example, currently neural network-based approaches. And we tend to, because science is a human enterprise, we tend to throw babies with the bathwater. That's just part of the deal. And so I try to look at some of those issues. So there was this issue of what happens to explicit knowledge in a world where you think everything should be converted into a tacit knowledge task, which is like the Polanyi's revenge. And AI research, AI systems themselves have kind of become more, sort of ersatz natural science rather than an engineering discipline. If you look at some of the flagship AI systems, such as DALL-E's or the GPT-3s, these are not engineered in any traditional sense of the word, where you take credit for, mostly we are spending time trying to figure out what did we just do? What is this system going to do? And real engineers don't take credit. Real engineers don't take credit for emergent behavior, by the way. Biologists take credit for emergent behavior because they're trying to understand how the nature works, but engineers actually design things, right? So we are already far enough from an engineering discipline, at least in certain areas. And so there were some interesting comments about how the changing nature of AI research and how it makes us close to natural sciences. That might be worth thinking. I generally really believe that if you have an area that celebrates emergent behavior, it's probably not an engineering department, because I think very few civil engineers are so happy that the bridge they built to withstand Category 5 hurricanes also sinks on alternate Saturdays. You don't take credit for that. You are very worried. What the heck did I do that it's right now this room was singing, if you notice, right? We don't want that. We want the room to do what it is designed to do, not do anything else. And so anytime you see yourself taking credit for emergent behavior, you are not an engineer. There's nothing wrong with not being an engineer, despite the fact that we are an engineering school. There's nothing wrong with not being an engineer, because oftentimes we might be discovering how things work. In this case, we're just discovering how things that we put together without understanding work, which is a different kind of a thing. So, we do that. And, my research background, which I'll talk more about, is basically this human AI interaction, in particular, explainable AI systems. There's a bunch of my students there, and we talk about human-robot interaction as well as human non-embodied AI system interaction. I'll give you some details of that a little later. And then since since I'm here for the DA, I should say something about my IIT Madras story. I was from 1978. Anybody born before that, other than, I don't know, is there anybody here who was around at that time? Certainly, long back. I was initially in mechanical engineering. I was in Alakananda. Yesterday night, I was walking around the campus trying to figure out what was going on. And then I was in Jamuna. And then finally, I went to Tapti for the last 3 years of my electrical engineering. So I'm actually an ESB guy. So I took a picture in front of ESB, although I'm like a computer scientist by profession now. And actually, I didn't have bothered really changing from electrical to computer science, because AI is now, it's neither here nor there. It's both electrical engineering and computer science. Discrete math versus continuous math. We're back to squarely to continuous math. Anyway, that was the only surviving picture of anything that I did here, and that's me. And that was in CLT. And then I did I got my degree, and one of the things that is connected to this talk is my undergraduate thesis was some experiments in isolated word speech recognition with Egg Narayana. Egg Narayana actually joined. Many people that you have seen as like the old wizened folks, they joined at the time when I was there. Like Ashok Jhunjhunwala taught his first class to our batch. And basically, he just came back and he taught communication theory. Egg Narayana joined from ISC, and he was a very research-oriented guy. He caught a bunch of us and started asking us to do projects and so on. So that was my undergraduate thesis. So speech recognition is AI, whether you call it signal processing or AI, it's AI. So I would say I'm in AI from at least then onwards, except it wasn't as much fun being in AI in those days. I mean, right now, everybody better be in AI. They'll just say, we are doing AI and material science. We are doing AI and mechanical engineering. We are doing AI and chapatis, whatever. So so the point being that everybody is very happy to be associated with AI. When I was associated with AI, all my friends would feel sorry for me. They thought, how couldn't you find something more interesting, such as databases or software engineering, all these happening kinds of areas, even within computer science. And in the area itself, for example, mostly people were thinking, why the heck should we even be doing this? And there are all these philosophical objections as to whether AI was even feasible. These were the kinds of books that were being written. As it was like people are leaving World Trade Center, and people like me are going in, to actually work in the area. So obviously, it's much different now. As Ravi said, I got to hang around with bunches of people in different places. Like that was the Netflix show. I have an IMDb rank. I don't have a Wikipedia page yet, but I have an IMDb rank. Okay. It's falling, so hopefully some Balachandar movie or something. Is Balachandar even making movies anymore? Okay, that tells you how old I am. Anyway, so I got to see actually Sushma Swaraj run an AI panel. That was kind of fun. And then that I won't talk too much about because it was White House, except with different people in the White House than I would like to be associated with. But anyway. So the thing that actually changed, and it's kind of useful to set the stage, is the thing that changed about AI is sort of the kinds of problems that came to the forefront, that the field is looking at. Intelligence itself is multifaceted, right? For example, kids come into this world doing perceptual, manipulation, reasoning, then they show emotional intelligence, then they show social and communicative intelligence, and then they do JEE, right? Right. I would say sad, but we are kidding. I mean, JEE, that's really the thing that people want to do in terms of cognitive reasoning intelligence. And the AI systems, humans, babies do that way, essentially, right? Human babies are animals first and people later, okay? AI systems were people first, animals only much later. So in fact, if you look at the way AI systems went, it was the original revolution is all about cognitive systems and expert systems, reasoning and so on. Deep Blue basically doing reasoning without knowing how to even recognize a piece on the board. It can actually come up with complicated chess moves and so on. And then only more recently we started going into this perceptual reasoning stuff, and that's now become the thing essentially, right? And we could actually spend some time on that. I won't do too much of it, but it makes sense to understand what's going on in AI if you actually just realize that there's this distinction between how human babies developed, typically in the intelligence and how the AI systems worked. Okay, one particular thing is that many of these lower level ones, cognitive reasoning intelligence, these are civilizational tasks for which we have explicit knowledge. There is actually a way of doing differentiation. You don't just wait for differentiation to kind of sink in. You take courses to learn differentiation, for example, right? And so this sort of a thing, if you know how to do it, you can then program the computer to do it, which is more or less what original AI revolution was all about. I mean, so you can program it. In fact, people used to say that when you can program, then you understand even more, right? Now I can program DALL-E to make pictures. Do I understand pictures anymore? Not at all, right? There is a difference. That statement only holds for explicit knowledge tasks, the ones for which we actually have an idea of how to do the task. When you actually write down a program, then you kind of have a way of debugging whether or not your theories made sense and so on. So that was the way we were focusing on those things. And when we get to the perceptual and manipulation tasks, I mean, obviously, there was no theories, there was nothing to write programs about, so the only thing that's left in the room is learning from examples, right? And the same way kids were doing, essentially kids were not being taught by a mother, this is how you recognize your mother. If such kids existed, they are dead long back, right? Because we don't know how to communicate, how to recognize anything, more or less. Okay, so that sort of a thing, it's easier to program computers with explicit knowledge tasks, and there was a lot more of the explicit knowledge tasks that were being considered. Now it's all about the tacit knowledge tasks that are being considered, and the problem is human intelligence is a beautiful combination of both explicit and tacit knowledge tasks. We do things that without understanding, but civilization itself progressed because we can make contestable decisions that we can actually, explain, we can, disprove, etc., etc. There's some kinds of things on which you don't ask for explanations, like how do you walk, for example, or how do you see a picture. But there are other kinds of things where you decide that a defendant is guilty, you better give a reason, for example. Otherwise, we would not have, a civilization. And so that is kind of a useful thing to keep in mind. And that Polanyi's revenge thing, a piece that I mentioned earlier, essentially was sort of talking about the fact that the baby that got thrown out with the bathwater when we started taking into account the tacit knowledge tasks, which is very important because computer systems sucked at doing vision. Computer systems sucked at doing language before the advent of neural networks, in particular deep learning. That is great, and you need those abilities. But you also need the reasoning abilities. You need the civilizational tasks for which we have explicit knowledge. If you cannot have the system do what you want it to do, and then just hoping that the system magically figures out what you want, can have all sorts of bad consequences. If you hear all the angst about bias in AI systems, etc., it's like you're thinking, why can't the system figure out from the Reddit data and the 4chan data what is a good way of behaving in the world? I mean, the joke is on you, not on the system, because essentially we say that, but we also have civilizational mores about what is actually the reasonable things to say and what's not reasonable things to say. And so basically that piece was talking about the fact that if you ever find yourself trying to take a piece of knowledge, converting it to examples just so that you can learn the piece of knowledge back, don't do it, because that's like nonsensical. Why are you doing it? I mean, there better be a very good reason why you are doing that, because instead of from data to knowledge, this is knowledge to data back to bad knowledge, right? If you happen to know how to do this thing, and you just, because your system doesn't know how to deal with anything other than examples and pictures, you convert your knowledge into pictures or examples and then feed it to the learning system, then there is something wrong. Okay, so it's worthwhile keeping that in mind, and so that's sort of a useful thing to, that was one of the points that was being made. But that's all about the general field. I want to talk about just the work that I'm doing right now, at least for this talk, some technical parts, since mostly CS audience are there. Given that, for better or worse, we are surrounded by AI systems, right? We want to be able to communicate with them the way we communicate with each other. So we should be able to ask for explanations as to why did you do a decision. We should be able to advise them, saying you should do this particular behavior, you should have, modify your behavior in the following way, for example. These kinds of advice and explanations should be done in terms that make sense to us, which is what I was saying in the very beginning, which is basically, for example, the natural modes of interaction. One big one of which is symbolic interaction, okay, linguistic interaction. And so explainability and advisability must be on our, that is human terms. We shouldn't have to debug AI systems to interpret them. It's kind of sad, right? Because we are now increasing our difficulty of dealing with our world rather than making it better. And it would be a pity, as I said, if all the progress in AI results in us going into the incomprehensible land of the AI systems. The heavy lifting should be the other way around. The AI system should be citizens of our world and talk in the language. I mean, if you go to Germany, they are not going to talk to you in Tamil, surprisingly enough, okay? You learn German, right? And so if you go to human land, you learn to speak in words and vocabulary items that make sense to humans. So we argue that AI systems need to support a symbolic lingua franca with the humans in the loop. And in saying this, since I said symbols and neural in the same slide, some of you might be thinking of this new buzzword that has taken by a storm, which is neuro-symbolic reasoning. Okay, and it means lots and lots of things to lots and lots of people. I want to differentiate two very specific meanings and say that I am about one particular piece. Okay, so neuro-symbolic reasoning can be about systems' internal representations and reasonings. Okay, that they should not just have neural networks as their representations, they should also have logical rules. They should also have some, instead of neural networks, maybe they should have decision trees, because that somehow has interpretability guarantees or something. Okay, that is the internal symbolic reasoning. Okay, I'm not going to argue one way or other about it. Okay, I mean, I can argue, I can have a religious war about that outside of the talk, but talk is already short, that I'm not going to argue on that. There is this other one, which is a symbolic communication interface, which is external symbolic. So I don't really care what the internals of the system are using. Is it using purely neural, purely symbolic, or neuro-symbolic approaches? Because humans are in the loop, one of the modes of interaction with them has to be in symbolic terms. And they should be able to take symbolic advice, and they should be able to provide symbolic explanations. What that means is what I had to do when I came to IIT, which is, before I came to IIT, I never spoke a word of English. Okay, I basically somehow took my intermediate exam in English medium, but I never spoke English. So when I first came and I was going on a bicycle, some people will say hi. And I had to very quickly translate hi into my internal Telugu representation, and then figure out, do a lot of Telugu reasoning to figure out what is an appropriate meaning, appropriate response. And I will come up with an answer back, by which time those guys are gone. But I had to essentially take the communication, convert into my reasoning, and then get the response back. So there would be sort of a on-demand translation that the system has to support. But the translation is done by the system, not the humans. The humans will speak in symbolic explanations requests as well as symbolic advice. Okay, so that's what we'll be doing. And again, I said, one big reason I think symbolic communication becomes important is that regardless of the internal reasoning ability, you will need this, because in a minute I'll point out that if you want to explain decisions or take advice, and you have different brains, as you would have with you and your AI system, then the question becomes one of what is the common substrate? What is the substrate that you share? Okay, if you don't have any common vocabulary, right, then all you're looking at is a single picture in front of you, and then maybe you can say, why do you do this? You sort of pantomime some part of the region of the picture and say saliency region. Saliency region is like what you would do if you haven't evolved. Dogs will do saliency region. There's nothing wrong with dogs, but how many of you are dogs? How many of you want to become dogs? Part of what civilization is that we can essentially explain over, it's not even the pictures. In fact, when I ask a question about a sequential behavior as to why do you do a particular decision at a particular point during your behavior, I then need to provide that saliency explanation over a space-time signal tube, something like some generalized video of my life, and say, these pieces, these pieces, these pieces. Capish? And that's a pretty bad way to explain. And in fact, if we had to explain like that, we would have been just as successful as dogs. Okay, we figured out a way of explaining things to each other in symbolic terms, and that's what we basically wind up needing for the AI systems to interact with us. And so that the thing that for the next few minutes, what I want to do is to kind of give some technical details at the level that might make sense to you on mental models in explainability. First of all, when you're actually explaining anything to anybody, explanation is about other people's minds, not about you. Right? You understand that. I mean, those of you who are teachers or bad teachers, or those of you who have seen bad teachers know that people who talk to the blackboard or the whiteboard are basically not talking to the students because they have no mental models of the students. Okay, so explanations are about the mental models of the receiver, and so then you can talk about explanation as reconciling mental models. Getting the mental model that the human has about the robots or the AI system's capabilities closer to the true capabilities of the robot. We'll talk about that first, and then this kind of generally, we have done a bunch of work. I have a book on this for the case when essentially both the mental models of the human as well as the model of the robot can be represented in effectively symbolic terms, which means the vocabulary is similar. And then you still have to do reconciliation of models. And that part we have done. There's a bunch of papers and there's a book. I'll quickly mention that. And then I'll go into what happens if you do not have a common vocabulary, and how do you actually, what is involved in actually generating explanations on the fly in terms of a symbolic vocabulary after the fact. That means you have done something and then you are providing an explanation that makes sense in the terms that you share with the human. And similarly, if the human is providing advice and you are some sort of a pixels to decisions, deep reinforcement learning agent, then how do you take the symbolic advice and make it affect your reasoning? Okay, so those are the things that, and for that I'll talk about a couple of papers that we have, more recent ones, Eclair and Eurips and ICML papers, and one on explainability, explanations, and the other two of them are on advice taking. And then I also kind of talk about doing this in a more general sense, what are the general research challenges depending on the time. And in fact, this came out, in addition to these papers, we wrote a blue sky paper for AAAI, so kind of the talk is fashioned off of that. And then I'll conclude. Okay, so mental models and explainability. So first of all, what does it take for an AI agent to show explainable behavior in the presence of human agents? And I would argue that first thing you need to understand is mental models. Okay, it actually, how many of you know Sally-Ann test? Okay, only one person. So it's probably not surprising because it's an engineering school and we don't mental model. But it's actually one of the very important social skills. Mental models are connected to social skills, and this follows the trope that engineers don't have social skills. But the point that I'm trying to make is that in Sally-Ann test, this is the question. Okay, this is a JE level question. Okay, think about this very carefully. So the Sally is in red and Anne is in blue. Sally comes in, puts the ball in the yellow box, and then Sally walks away. Then Anne comes in, takes the ball from the yellow box, puts it in the gray box, and then Anne walks away. And you're seeing this. You have nothing else to do. This is just an evening, so you're seeing this stuff going on. And then now Anne has come in, and she's going to look for her ball. The question is, where will she look for her ball? Do you understand what I'm saying? And if those of you who are having trouble, you have major social skills problems. This is why the world doesn't seem to make sense to you. Because if basically most of us, most of the normal people will realize that Sally will look for her ball in the place where she put it. The fact that you know that the ball shifted doesn't change Sally's knowledge of where the ball is. Interestingly, when kids come into this world, there is psychological research showing that in the beginning, they tend to think that their body is connected to the entire universe. They don't actually differentiate themselves versus the rest of the world for the first few days or something. And then for a while, they think that they get out of that and they realize they have an independent body. And for a while after that, up until 3 years of age or something, they tend to think that what they believe and what they know is known to everybody. That's why Sally-Ann test is developed, to actually check the social skills developments of kids as well as engineers. And the idea is, after 3, they would realize that just because I know something doesn't mean other people know it. By the way, that's when the beautiful art of lying starts. You can't lie if you think everybody knows what you know. Do you understand what I'm saying? In fact, there's this beautiful statement in this book called The Boy Who Knew What? Did you say something? The boy who, something about this artistic boy, the boy with a dog or something, I forgot the name of the book. But so where he says, it's the artistic boy, he says, I don't know how to lie. At any given point of time, one thing happened. gazillion, trillion things didn't happen. Which of the many, many things that didn't happen are you going to actually pick to tell the lie? So in some sense, lying is actually harder. So I joke around that when my son told his first lie, I knew that his brain is working. It actually has the ability to mental model. It's not just whatever I know is what everybody knows. But the reason this is important is explanations are completely about mental models. If we all understand, if we all had the same hive mind, we will never ask each other any questions. Think about this. The only reason we ask each other questions is because we have different mental models of the task. That's why you think, oh, I thought it can't be done, why did you do it? If it's the same exact mental model, there is no reason to talk, there is no reason to ask questions, there is no reason to provide advice. Okay, so explanations are very well connected to the mental models, and this was essentially exploited in most of our work up, on last 6-7 years. Essentially, to understand that the minimum that I want you to understand for the rest of this talk is, if you think of a robot working on a task, it has a model of its goals and the environment, call that MR. The human in the loop might have their own goals and their own actions that they can do, call that MH. Because the human is in the loop with the robot, the humans will mental model robots. Humans cannot stop mental modeling. Humans mental model rocks, and they say they're gods, and they start saying the rock is mad at me. Okay, so all sorts of things that we do. So humans mental model everything, and so they're going to mental model the robot, and then they will essentially say MR. So I will call MRH is the approximation of the robot's model according to the human. And then when the robot is trying to make sense to the human, all it needs to make sure is that its behavior is consistent with MRH. If it's consistent with MRH, there's no questions asked. I would say that's explicable behavior, because that's what I expect you to do, that's what you did, so why would I ask any questions? When it's not consistent with MRH, then you either make it consistent or you have to provide an explanation to the human saying, please, pretty please change your mental model of my capabilities. You are thinking the following thing is possible, it's not possible. And an explanation is in essence changing the mental model the human has about the robot. An explanation from the robot to the human is changing the mental model that the human has about the robot. So the whole point of explanation is changing MRH, working with MRH. Okay, keep that part in mind, and it turns out that you can do all sorts of things based on that. So there's basically that was, I'm not sure whether it's working, but so there was a little video going on there. I don't know if it will work again. That you can basically have in this particular one, I don't know why it's not working, but so there what happens is that robot can, for example, either it has a short path to go somewhere, but it also knows that the human expects it to take the short path, but it's on the actual environment and the path is clogged, it's blocked with debris or something. So it's now going to take a longer path. So the question then is, it knows that its behavior would be unexpected to the human in the loop. So either it has to clear the debris and go through the closed path, which would be costly, but it will be explicable. And sometimes you want to be explicable if in fact if there are only two doors and they are like 200 miles apart and the human is waiting for the in this door, then you better spend time clearing up this path and get out of that path, right? The other would be providing an explanation which is trying to tell the human, change your model of the map that you think I have, and add the point that this particular path is clogged. There is actually debris on it. Okay, with that the humans will come in consonance with the robot, and in this particular question, in this particular case, they will understand the robot's behavior. Okay, so you can basically do a bunch of this sort of thing, and so we had you can talk about how to provide explanations, how to provide explicable behavior, what sort of explanations can you provide, can you handle multiple humans with different mental models about the robot's capabilities, all of this stuff that we do. Sometimes, for example, one of the things about explanations, as I said, is it about the receiver. So if you think of your doctor, a surgeon making a decision, a medical decision, they will explain that decision to the patient in one way and to their own peers in a very different way, because you are basically given the explanation you can understand. instead of just be throwing, read the chapter 4.9.7 in JAMA. That will explain to you why I made the decision. That's not a good explanation for patients, because they won't understand that. Okay, so we did all that, and so there's a book on that, and that's like the older work. So coming to the addressing vocabulary mismatch, in that previous work, we tended to assume that essentially there is a vocabulary is common and the action representations are different. So for example, the difference between the mental models of the human's mental model of the robot versus robot's actual capabilities would be in terms of different preconditions and different effects for the same actions. And so the human might be thinking some actions are not feasible when they are actually feasible to the robot, and I might be thinking some actions are actually feasible when they're not actually infeasible for the robot. So these were the differences that you had to handle. But what if, in fact, the representations are such that, in fact, there is no common symbolic model that's being used, a common symbolic vocabulary that's being used, which is what I brought you to. And so first point to understand is, even if we share the language, we still have to explain to each other. How do you know? Ask yourself. Why do you ask each other explanations? You understand English. Mostly English means the same thing for all of you, and yet you ask for explanations. That's the model reconciliation. That's what we were supporting in the previous work. But now if you're doing the same thing with the machine, then assuming that the machine doesn't have any symbolic vocabulary, if it's like some kind of a pixel-based, pixels to decisions kind of a reasoner, then the question is, if you ask your Atari player, why did you make this decision? Can it give it in symbolic vocabulary? That's the part that we were focusing on. So explanations in the absence of symbolic vocabulary, I will skip over this because I mentioned this already. Show the simplest thing that you can do when there is absence of symbolic vocabulary is to look at the only thing that you share, the common substrate you share, and kind of do the saliency regions. Like I said, saliency regions don't scale, first of all. Okay, because if you want to do it for sequential decision problems, it's not saliency regions over a two-dimensional picture, it is saliency region over space-time tubes in at least generalized videos. And it will be one problem with explanation, one important thing about explanations is explanation should not only be given, but should be understood. Teachers think that they explain whether or not people understand. That's how you become a bad teacher, okay? But if you want it to be understood, you need to actually make sure that the explanation that you give is understandable to the human, the student in the loop, okay? So it turns out that saliency regions are like a very bad way, and they are not likely to scale. And in fact, so the question then is, pointing explanations in general are hard to comprehend. That's for the reasons I mentioned, and which is why probably we humans developed symbolic languages. Okay, if you think about it. Okay, so what humans seem to develop a shared symbolic vocabulary, exchange symbolic explanations where possible, and come down to pointing explanations only when the vocabulary is inadequate. Think about it. You will fall down to pointing as a primitive assembly language way of communicating, but mostly you will try to exchange symbolic explanations. And what is interesting is, even in essentially tacit knowledge tasks, such as if you are a basketball player fan, then pick and roll, which is a symbolic concept, or LBW, which is a symbolic concept in cricket, which can be misused in all sorts of ways. Generally, the way you hate umpires is, how the heck can this be LBW? Now, what is LBW? It's about actually a made-up symbolic term to describe some tacit behavior between that's happening on the page. So we would like to talk, even when there are videos available, we'd like to talk in language. It's that crazy we are. And so basically we will go back to pointing only when the words won't be enough. So we want to do this for the machines, and the things that you can do is the use case for symbolic layer would be that the symbolic model, sort of the symbolic interface that every AI agent has, is sort of customized to the human in the loop. Unless the humans are all of one category, it's customized to the human in the loop, and it essentially is sort of a way of thinking of MRH, which is the human's mental model of the robot's capabilities. And when the humans are asking explanation questions or providing advice, it would be in terms of that symbolic model, and it will have to be translated to be usable by the system. In one case, the system has to translate its internal reasoning to vocabulary. In the other case, it needs to translate vocabulary into internal constraints. Okay. So in the case of the first case, the explanation case, here is an example where the system might be playing this Atari game, and then basically the kind of explanations, typically the explanations that you would like to think about are, one big class of explanations is what's called the contrastive explanations, or file-based explanations. You will say, why this decision, why not this other decision? Okay, so this Montezuma's revenge, basically the user might be asking, why did you do this particular action? And the system has to provide a reason, typically by saying the action you are expecting me to do will be costlier or infeasible compared to the action that I did. In doing so, it is slowly, surgically changing the human's mental model. So if the humans are listening, if they are listening, then they won't ask the same question the next time around. Again, you can't stop people from not listening to your explanations, right? I mean, that's something that they can do, but at least if you provide an explanation, you are allowing them to change their mental model. Okay, that's what we are doing. So in this particular case, since it's reasoning, in this case, Atari game case is like a RAM state representation, not about these vocabulary items. How does it convert this? The simplest way to think about it, even though it's not technically fully accurate, is to say that the machine may well be thinking of the explanation in terms of a saliency region, but then it is approximating the saliency region in terms of some symbolic concepts whose essentially each symbolic concept may well be covering some part of the saliency region, and you are using that mapping to actually provide the symbolic explanation back. But essentially another way we wind up doing this is that in this particular case, the details are in ICLAIR 2022 paper, but what we wind up doing is the machine at the place where the decision is being questioned, it learns a local symbolic model about actions with preconditions and effects just in that region, okay, and then provides, once it has a local symbolic model, then it can do the model reconciliation using the previous work that we already have. Okay, so that's what it winds up doing, and to be able to do that, so some of you may have heard of LIME, which is one of these earlier explainable ML systems, which tries to learn a local linear model for a complex complex neural network, for example. Here we are learning a local symbolic model for whatever the heck you are doing for your decisions, and I'm basically then converting the model reconciliation in terms of this learned symbolic model. Okay, to be able to do this, how to do the reconciliation, that's actually sub-goal to that work that I have shown earlier that we have completed already, so you can actually use that. The other question is, how do you actually learn the local PDL, local action model? For that, you need to essentially have a shared vocabulary. We'll assume that we start with some shared vocabulary with the humans, and then you learn the denotation of the shared vocabulary with respect to your representation upfront. So that's almost a subroutine which is amortized. Once you understand the meanings of those terms in terms of your pixel space, then you can reuse them every time when you are converting the explanations into symbolic terms. Okay, and then once you do that, then learning action models is essentially in terms of fitting preconditions effects to the known actions. Remember that the actions are common between the humans and robots, even if the representations, internal representations are different. Okay, so the only question then would be figuring out the preconditions effects. So the robot figures it out for the human, which is the way it actually computes its MRH that the human might have, which would have allowed them to ask this kind of a silly question, and then tells them why the file is not a real file. Okay, so that's basically what we wind up doing. And one of the interesting things in doing this is that we can also actually as part of this explanation, we can also construct sort of confidence level of our symbolic explanation. One thing that people are worried about is this is a post facto explanation. You did it one way and you are explaining it in a different way. come to the real world. That's exactly what you do every time. Okay, if anybody asks, if you really want to be accurate about how you to explaining why you did whatever you did, it involves lobotomy, essentially. So basically, people ask, why do you do it? Take my brain, figure it out yourself, which is pretty painful, right? So you always ultimately provide a post facto explanation, and of course post facto explanations allow for lying. In fact, there's a paper that talk about, we have a paper in AIES which talk about, once you have mental models, as I said, kids with mental models can tell lies, AI systems with mental models can tell lies, right? And so the question is, they can tell white lies, for example, and would you be, and the whole most of the human civilization, a lot of human civilization depends on white lies. If somebody asks you, how do I look, don't ever give the real answer. Unless you are their personal beautician or something. The answer is always great. Okay, and that's a lie most of the time. For most people, it's a lie. And but the civilization fabric is not torn because you tell these lies. What if your AI system says this to make you feel happy? So we have actually a paper in AIES in 2019 or something, talking about how the ethical implications of this, and also whether or not humans seem to be okay with being told lies by other humans versus AI systems. Okay, but my point is, explanations and lies are connected, and you cannot just say there is no we can't do post facto explanations, because all explanations are post facto explanations. You have to essentially convert the reason for what you did into terms that make sense to the other person's mental model, which may very well be the reason you did this might have something to do with Riemann's hypothesis, but the kid who's asking the question is your 2-year-old nephew. Telling the 2-year-old nephew an explanation in terms of Riemann's hypothesis, unless that kid already passed JEE or something, is like a dumb thing. Do you see what I'm saying? You are going to water the explanation down. But and then you say that's post facto explanation. But if the kid learns something from that, that's a very useful thing. So it's basically something that we do. So the question, of course, is, since we are converting the saliency region to, for example, a symbolic model, and then converting that into explanation, the question would be whether, how confident are you of the translation? Roughly speaking, imagine the saliency region is irregularly shaped and you didn't cover most of the region with the explanation that you provided. In that case, you can actually compute the confidence, internal confidence. The machine can compute the internal confidence of its own explanation accuracy, and that can be used, for good ways, because you can actually say this is an explanation, but this is the level of confidence of this. So you also tell this to kids, right? Like, the real reason is complicated, but here is an explanation that you will understand. Okay, that's something that we can do with this. And then we did actually studies with humans, human subjects, and of course, human subjects are happier to be given explanations in symbolic terms. It's not surprising, but we did an IRB sponsored actual human subject study. Accepting advice is the other part of the coin. Human user can directly update the model to drive the system behavior this way, to be closer to their preferences, to be closer to what they think is the real dynamics of their model, for example, etc. But these modifications have to be translated into a form that the underlying system can use, right? But the translation should be done by the system, not the human. So you provide the higher level advice. This is what happens. You have advisors. Some of you are doing research. You have advisors. Advisors give higher level advice, and then you are operationalizing it into how to actually drive that advice into your reasoning. And that's something that you are doing. If you tell the advisor, no, write the paper, damn it. You don't tell me the high level advice, that's when I know that you know what you're talking about. You won't have an advisor, right? So, so accepting advice essentially can be given either during the learning time, when the RL agent specifically requests. So here I'll assume that the agent taking the explanation mostly to make Ravi happy is a deep reinforcement learning agent. Okay, it could be any AI system, but imagine, since I'm into sequential decision making, deep reinforcement learning agents are a good stand-in. And so the advice can either be given during the learning time, where the RL agent is specifically requesting for criticism about its evolving policy, saying, is this an action to do? Is this a good action to do at this point? Okay, the old human in the loop RL work which was mostly there when people were, the RL systems were like too inefficient and people had time, actually used this sort of a feedback mechanism, and you can improve the overall efficiency. But really it can be used this day and age. It's not for the efficiency, but to give your preferences to the agent. In fact, the quote unquote alignment problem, what is an alignment problem? The machine is providing a policy that works according to its model, but that's not something that makes you happy, because you have additional constraints that the machine hasn't figured out, that you haven't yet told it. And so you are providing these constraints out front. Okay? The other possibility is, even before the RL phase starts, via an incomplete model of the world that I have, that the human has, they can provide like a symbolic model that then drives the RL. This is sort of, think of model-based RL, except, partially the model is initialized with the human given incomplete model. And so both of these were done. This one is a Nurip's paper, this was an ICML paper. I want to give you a quick outline of what is happening, and then we will stop. So in the case of the taking the feedback, what we wind up doing is essentially, the idea is that the DRL system is going to say, okay, I'm doing this action in this state, okay or not okay. And basically the human can say not okay and provide an explanation. And that explanation would be in symbolic terms. Like, for example, I'm crossing this intersection, okay or not okay? Not okay because there's a pedestrian. And the pedestrian part doesn't make sense to the machine, because the machine is thinking in terms of pixels. Some pixels happens to be pedestrians, some pixels are just pixels. Okay, and so it has to convert the pedestrian part of the explanation into sort of its internal saliency region, and then drive that to actually do better policy learning. That is the thing that is done in this work. In fact, one other cute thing that winds up happening in this work is, when you provide an explanation saying pedestrian, and the pedestrian corresponds to some saliency region that the machine has converted to, then it knows that the rest of the state can be changed outside of the saliency region, and the action's explanation might remain the same. And so you converted one feedback cycle into multiple feedback examples. So it's sort of, this is augmentation of feedback. Okay, so we did that, and actually that improves the leverage of the advice that the humans are giving the machine. So that's one part of it. This is a context-aware data augmentation, which is basically expanding the one feedback into multiple feedbacks. There are experiments showing that this kind of thing improves the convergence as well as make it closer to the human's preferences. That's the things that we want the advice. The other thing, the last thing that I want to talk about is, you can actually provide like a partial symbolic model. You don't quite know how the domain works, but the human provides a partial symbolic model in, let's say, PDL or some strips level language. It's wrong. I mean, it's not complete. It's not guaranteed to be correct, but it becomes weak heuristic guidance to the RL system. Okay, and the way to operationalize it is done by the machine again. So in our case, the way we do this is, we take this partial model, and the machine takes the partial model, learns what are called landmarks, which is, if you're trying to reach a goal, and if this is the correct model, then you would go through the following states. Okay, and then essentially it turns out that the actions you do to go through those states in the partial model may not be the correct actions, because there may be more details that have to be actually done in the real world to actually go from that through those states. Okay, so then the RL system essentially uses these landmarks as like sub goals, finds options to get to each of these landmarks, multiple options, and combines those options. I mean, I'm taking the advantage of the fact that more of you know RL. I'm saying that you're essentially computing sub plans for people who are talking about planning. It's sub plans for the sub goals, here options for landmarks, and you can then combine the landmark options to get a overall policy. And doing so can be significantly more efficient than essentially the machine starting from scratch at the lowest level of abstraction. This will work as long as that, essentially, I mean, theoretically, if you say if the advice is wrong, will it still work? And the idea is that under fairly weak conditions, which is that if there exists even one single trajectory at the real world which goes through all the landmarks and reaches the goal, then this will be working. That means you will not be losing losing completeness. But I say this with a huge grain of salt, because nobody cares about completeness these days anymore. In the old days, people will actually prove completeness for problems. Now you draw curves saying it used to be very inefficient and it's less inefficient. And one of the greatest things, again, about deep reinforcement learning systems from pixel space is they're so inefficient to begin with that anything improves the performance. So for every possible idea, you can write a separate paper. Okay, that's a good way of, possibly, cynical, but a true way of thinking about it. Okay, and so any advice is actually good advice most of the time. If you don't know how to solve the problem, you ask your friend, they'll say, oh, maybe try this. And that you will, you won't say, are you sure this is the correct advice? You're flailing. The guy at least gave you the time of the day. You take it and run with it. That's basically what is happening. Now, having come to this, actually, if you replace the human giving this model with an LLM, think of human as an LLM, and you ask the LLM, how do you do this planning? How do you do this problem? Okay, people are trying this. Okay, and it turns out, I don't have the slides here, but I have a paper showing that if you ask LLMs how to do plans, the answers, the performance is like ridiculously bad. Large language models. So large language models, basically, large language models are like a poster child of emergent behavior. They were essentially generated to, given a huge if you learn over a huge corpus, can you predict the next word, right? And then it turns out that they seemingly have these additional properties, such as kind of, making reasonably coherent text, coherent as judged by us. We have very weak standards. I mean, we read people's papers and we think they are written well. And so now GPT is writing them. And so we have, so GPT can be asked, some people asked, zero-shot learning is a big thing. That means you don't tell anything to the system and see if it already knows it. If so, you get to write a paper. This is like the best way to do AI these days, right? So zero-shot, there is actually a paper called Large Language Models Are Zero-Shot Reasoners. Well, my little kid, when he was half-year-old, was a zero-shot reasoner. But his reasoning was flawed. Do you see what I'm saying? That's what happens in the LLM. So if you actually take their plans at their face value, and you actually check whether they can be executed, they will have, in the test that we did, they have 0.6% accuracy. Even NeurIPS has higher standards than 0.6% accuracy, for planning. But that looks like a bad thing about LLMs. But imagine LLM is like your advisor. Advisors don't know how to write papers, but they can give you high-level advice, and maybe if you follow that, maybe you'll get a paper. That's what was happening in this part of the talk, where the high-level model was possibly incomplete, possibly incorrect, but you can actually use that to give direction to the search. If you view LLMs as a source of weak heuristics, and it's actually a pretty complex domain, it can actually improve. It can show improvements in deep reinforcement learning's performance, which is the best thing to show improvements on, because it's actually, most of the time, RL is quite slow. Okay, and so that's a kind of a connection that you might want to keep in mind. So as I said, MVTR is a property that if it holds, it actually has also completeness guarantees. And the other thing, of course, is the landmarks. You actually wind up learning diverse skills, diverse options, and then combine one option from each to get a overall policy. The experimental evaluation show that things improve quite well. I won't actually, it turns out that even if in fact you're doing human demonstrations, if I'm miming, okay, if I'm now miming some movie name or some song, the way you interpret my mime depends on the shared symbolic vocabulary. Do you see what I'm saying? So it's not even, so even if in fact what is being shown is demonstrations, parsing the demonstrations, making it less ambiguous, depends on having some shared vocabulary, shared symbolic vocabulary. And so in fact, there is a paper by another student in a AAI workshop which shows that, the explaining the parses in terms of shared vocabulary significantly reduces the ambiguity in parsing the demonstrations. And so that's the same again, the idea that you are potentially conveying, I'm not just dancing, I'm trying to convey information to you. And the information has to be in terms you can understand, and that means it must have been part of the shared vocabulary, right? That winds up being useful. So that's the talk, and then research challenges. It turns out that, as I said, collecting initial concept set is a thing. Obviously you could always say you could get all the concepts up front and get their meaning, and then, that's a kind of broad, shallow models that we would not even consider doing before. But in the age of LLMs, that is a possible direction too. In our own work, we assume that we start with some, partial, some set of concepts, and then you expand it as needed, okay? So collecting the concept set, grounding the concept set is a basic learning problem. You are essentially, it's a separate learning problem, right? Which essentially you're saying you're trying the meaning of each of them in terms of, for example, salience regions, okay? But that work is amortized over all the later interactions, including explanations and advice taking. Vocabulary expansion is interesting. There are two ways vocabulary expansion can occur. Sometimes the machine can realize that the confidence of approximating its, for example, the saliency region with the symbolic concepts is too low. At which point it realizes it needs more concepts, more symbolic concepts to actually give the real reason, So at that point, that can lead to a dialogue to expand the vocabulary set, that the human knows the vocabulary, but it just wasn't part of the initial shared vocabulary set. That's one type, okay? That can be done. We haven't done this yet, but that is actually more feasible to do. It's sort of vocabulary reconciliation. It's not just model reconciliation. You realize that you are missing some words to actually provide the real reason, okay? The vocabulary reconciliation there went from the human has the word and you're just trying to get it into the set. The other more interesting version is the vocabulary reconciliation where the human doesn't have the word and the machine is saying you better make one word up. That's the kind of thing that happens in AlphaGo with that infamous 37th move where everybody says, hey, it worked, why did it work? And the reason is that to explain why it works, you need new terms. Okay, just like pick and roll or something, okay? And so there was some work that was done where basically that, I think the DeepMind guys and Bean Kim, who's another person who works in this area, which essentially talks about how to support that sort of vocabulary expansion, where the machine becomes the teacher, saying, really, I have this thing I'm trying to teach you, but you need these extra pieces of vocabulary. So let me first teach you, let's get that squared away. In some sense, student-teacher interaction goes that way. Right? Because before I explain something at a higher level, I need to first get you to that level that might be teaching. So that's the thing. So summary, I argued that the AI system should support a symbolic interface for communications with humans, independent of whether their internal operations themselves are in symbolic means. And I kind of discussed the research challenges. I gave you some examples of the recent work that we have done about doing that sort of a translation. In the long term, the symbolic interface might morph into a symbolic persona for the systems. And this is an interesting philosophical question. Are we purely linguistic or not? It's clear that language developed much later. Language developed after, much later in the evolutionary chain, right? But we do talk about things like the limits of my language are the limits of my world. So when you kind of develop the symbolic means to interact with each other, eventually we became symbolic beings to some extent, okay? It's late in the day to get into that philosophy, but it's possible that the AI systems, when I first kind of cleverly get them to start having a little symbolic interface, will become symbolic beings later on. At which point, the internal symbolic versus external symbolic goes away, okay? But I'll leave that for a different talk, and thank you for your attention. Sure.
So now this
Thank you. Thank you. Thank you all again for your patience.